Thanks, Jessica. Thanks, everyone, for coming to my talk after all the party last night. So I'm Ruta, and I'm now a researcher at Facebook Reality Labs, where I work on adaptive interactions for augmented reality. But for today, I'm really excited to share with you all some work from my PhD at Carnegie Mellon on expressive robot behaviors. This is joint work with the awesome team at Autodesk Research in Toronto. So what is Geppetto? Geppetto is a data-driven software tool that enables users to create expressive robot motions based on the high-level and semantic descriptions of the desired robot motion. Using Geppetto, for instance, a user can convert a mundane and boring-looking motion of the walking robot into a more interesting and cheerful-looking one. Geppetto currently supports designing emotionally expressive robot motions, such as happy and sad-looking robot motions, for two very diverse robotic platforms, a walking robot and a robotic arm. Motion designs for 6 basic emotion categories, which were defined by the well-known work of Paul Ekman, are currently supported. While Geppetto currently only allows designing emotionally expressive robot motions, our framework and pipeline is useful for creating a wide variety of expressive robot motions. So before I talk about how we build Geppetto and how it really works, let me answer some burning why questions that you might have. First, why expressive robots? And secondly, why do we need a design tool to create expressive robot motions? The animation industry has long shown us the value of expressive robot motions, expressive character motions, and what they could do for inanimate objects such as robots. And now that robots are becoming more prevalent in social and collaborative settings, expressive robot behaviors can enrich our interaction experiences with them. While the value of expressive robot motions is apparent in entertainment and consumer settings, even for other collaborative settings such as manufacturing, expressive robot motions can be useful for conveying meaningful task-specific information. For instance, a robot arm that is working with fellow human workers can do an alerting motion to ensure that the human workers are out of its way before doing a dangerous operation. Here is my final plug for expressive robots and what they could lead to. This is a beautiful robot exhibit in a museum called Mimus, and it is expressively engaging and interacting with people around. Unfortunately, creating such expressive robot motions is very challenging because it requires a lot of domain knowledge. One needs to understand about the robot's physics as well as about various parameters that need to be tweaked to create the desired motion. And the space of these parameters is very non-intuitive and high-dimensional. One also needs some understanding about what it means to convey expressions with motions. We can also, unfortunately, not really automate this process, and that is because the perception of expression is very subjective. So we really need to keep the designers or users in the loop and capture the user's intent about the desired motion, which may depend upon the motion's functionality or the context of the application. For instance, I'm showing 2 examples of a happy-looking robot here. If a user is interested in creating a happy robot, it will be hard for the system to know which one the user really prefers. There are many existing tools out there for creating robot motions, and Geppetto is also inspired by the strengths and weaknesses of these existing tools. These tools can be categorized into roughly 2 classes: animation tools and robotics tools. Animation tools have very rich editing controls, but most of them by default do not have any simulation capabilities, which is essential for ensuring feasibility of robot motion in real world. Robotics tools are on the other end of the spectrum. And that is why when we interviewed human-robot interaction researchers during our work, we found that most of them ended up writing their own software for their applications. Geppetto tries to fix this problem by combining the best of both worlds. It combines editing power with simulation capabilities. In fact, it takes a step beyond and tries to reduce the domain knowledge required in creating robot motions by leveraging semantic editing. As the name suggests, semantic editing allows editing designs by specifying semantic properties of the designs. This idea has also been explored in other design domains, for instance, to edit 3D models of images based on their visual, semantically described appearance. Geppetto aims to do this for the space of robot behaviors. Let's now look at the nitty-gritty of Geppetto as a system. Geppetto is powered by a semantic mapping framework that maps the low-level motion parameters of a robot to the high-level semantic properties of the behavior. We start with a parameterized motion dataset synthesized in simulation by randomly sampling the parameters, and then we use crowdsourcing to evaluate the motions in our dataset. Crowdsourcing gives us expression quality ratings for the motions in our dataset, and we do this for each and every expression category that we are interested in. So these are the 6 emotion categories in our case. Then we use regression analysis to map the expression quality ratings that we obtain from crowdsourcing to the low-level motion parameters. The functions that we get out of regression can then be used at design time to provide guidance. I will walk through each and every step of the framework using the example of the walking robot. So let's start with dataset synthesis. To synthesize the dataset, we leverage a physics-based simulation which uses trajectory optimization to generate robot motions. And this simulation is driven by a set of parameters. To figure out which parameters to embed in our simulation, we looked at the research in effective computing community because we wanted to ensure that these parameters can generate expressive robot motions. For the walking robot, these parameters were the pose of the robot, which are the relative joint angles of the robot, the speed of the robot's center of mass, and something called gait patterns. Gait patterns encode the way in which the legs of the robot move up and down during a periodic walking cycle, as well as the time each leg spends up in the air versus down on the ground. So pose and speed are continuous, and gait patterns are discrete, and all in all, we have 11 parameters. Thus, our design space or parameter space is high dimensional and is mixed in nature. So it's a mix of continuous and discrete type of parameters. By changing pose and speed, we can create variations such as these: a spread out, slow moving robot versus an uptight, fast moving robot. Similarly, by keeping everything fixed and by just changing gait patterns, we can create variations such as these. So we sample various motion parameters and record the corresponding motions. So we have videos of these motions, and that is really our data set. Now that we have our data set of motions, to capture the perception of expressions of these motions, we use crowdsourcing. But since the perception of expression is subjective, we represent it with a Gaussian, with a mean mu and a variance sigma. Our crowdsourcing was done using Amazon Mechanical Turk, and this is how our Turk interface looks like. We asked our Turk workers to evaluate pairs of robot motions for a given expression, and they were asked to pick up or select the motion that better expressed a particular emotion. They could also mark the motions to be equivalent if they are ambiguous. We then use a video game rating system called TrueSkill from Microsoft to convert these pairwise comparisons into a Gaussian score estimate for each motion. After crowdsourcing, thus, we will have a set of 6 Gaussians for each motion corresponding to the 6 emotion categories. As an example, for a sad-looking motion such as this, out of the 6 Gaussians, the Gaussian corresponding to the sad emotion would have the highest mean. While our data set was relatively large, around 670 samples for the walking robot case, I've pulled out the top-rated robots post-crowdsourcing for different emotion categories to give you a glimpse of it. Now that we have a set of motions represented by motion parameters, let's call them phi, and corresponding expression scores from crowdsourcing represented by mu, we can learn a function f that maps the n-dimensional phi to the real valued mu. And we use regression for this purpose. We experimented with various regression techniques, starting with the simplest linear regression to the most complex neural network regression, and a bunch of others such as random forest, k-nearest neighbors, kernel regressors, etc. We found that neural networks worked best in practice, so they gave the highest accuracy on our data, but neural network regression was also expensive to compute. Linear regression, on the other hand, came close in terms of accuracy and was much faster, so we used that within our interface. Here is an example fit on test data using linear regression for happy scores shown in orange, compared to the ground truth scores. These are the values from crowdsourcing shown in gray. Since crowdsourcing data is noisy, we also downweighted samples with higher noise during regression. And that is why the orange line fits the high-quality samples, so samples with higher rating, relatively better. The regression functions power the two main semantic editing features in Geppetto. The first one is called automatic slider, and it allows users to edit the semantic properties of the motion without worrying about the low-level motion parameters. So for instance, by dragging the angry slider, the user will be able to make the robot move in a more or less angry manner. Secondly, to support the editing of low-level motion parameters, which is essential for finer editing control, we provide data-driven information about the effect of each parameter on the resultant motion of the robot, as well as the robot's expression. So these are the red curves you see here, and they are shown for the expression of anger. These curves are really what we get from the regression. So let's zoom into one of them a bit. Let's zoom even more. Here is a parameter editing slider for one of the parameter, rear knee angles in this case. So by changing this slider, the person would be, or the user would be able to modify the knee joint angle. Here the blue cursor corresponds to the current parameter value, while the dotted line corresponds to the system's prediction of the expression quality of the current motion. The red curve then shows how the expression quality would change by modifying that particular parameter. So the user can look at this curve to figure out how to modify this parameter. We also show a shaded band around the curves, which shows the system's confidence in the provided guidance. And this is again because of the noise in our data. We found that by providing such confidence information, we were able to provide more transparency and support better mixed initiative design. In particular, during our user study, we found that these bands encourage user-driven exploration in the spaces of the design space that had more uncertainty. So let's put all of this together. This is how our interface looks like. In the center, we have the main robot powered by the simulation, and on the right, we have the slider panel. We also use the data set to show an example, to show a set of example motions on the top, and we call this a motion gallery. So the users can browse through this gallery for inspiration and load a particular motion for further editing. We found that many times users had no idea about what sort of motions can convey a particular expression, and so by showing them the top motions from our data set, we were able to support such users. A typical design session in Geppetto begins with users selecting the desired emotion category for which they want to create a robot motion. This updates the motions in the gallery as well as the information on the slider. The users can then use the sliders to edit the motion. Whenever they modify a parameter with the slider, the simulation updates the motion. So here the user is trying to create an angry-looking motion, and the user sees that the body angle has an effect on increasing the expression of anger. So user modifies that parameter, and we say that that makes the robot look more angry. So as you see, by looking at the curves, the user to some extent also gets some understanding about how the parameters affect the motion. To evaluate our system, we conducted a user study with 12 paid participants who had no background in robotics or animation. We asked them to design expressive robot behaviors using two versions of the interface: a simple parameter control interface with no motion gallery or information on the sliders, and our full-fledged semantic interface. They were asked to design emotional motions for 3 categories: happy, sad, and surprised, and they were given maximum 5 minutes to do this. But our main focus was on measuring the quality of motions that they created. And to do this in an unbiased manner, we again use crowdsourcing. Here are scores from crowdsourcing for designs from our user study, and higher scores correspond to a better expressive motion. We not only crowdsource participant designs created using both semantic and parameter control interface, but also best and worst designs from our original dataset that was synthesized by sampling. This allowed us to see if our system could enable design beyond the dataset, and we find that this is indeed the case. Designs created with semantic UI were rated better for all emotions. So here are some designs from the user study. They're really fun to watch. So a natural question for a data-driven framework is whether we can reuse data-driven information derived for a particular robot to enable design for a different robot. So we conducted some preliminary experiments in this regard. We transferred one of our pre-synthesized happy motion for the KUKA robot arm to another robot arm which had different degrees of freedom and link lengths. I'm calling this a snake arm because of how it looks. And we see that this transfer worked reasonably well. The transfer preserved the main characteristics of the motion, such as swirling and swinging, which gave the perception of happiness. We also used the data-driven information from the KUKA robot arm. These are the parameter curves to edit the parameters and create motions for the snake arm. And we see that this also worked reasonably well. However, such reuse of data-driven information for design across different robots really depends upon how different the robots are and the underlying motion parameterization. For instance, we would not be able to use the data-driven information that we obtained from our quadruped robot to design motions for a hexaped robot because of the 2 extra legs of the hexaped robot. We wouldn't know what to do with the extra legs. So in summary, Geppetto took a step towards enabling easy design of robot motions. To do this, we encoded the domain knowledge in a data-driven manner by leveraging simulation and crowdsourcing. We allowed users to specify their design requirements semantically and provided data-driven feedback to support user understanding and editing of parameters. Finally, design alternatives and transparent guidance to some extent allowed the users to interpret the system's abilities and led to a better mixed initiative design. With that, I can take questions.
Thank you very much. Are there any questions from the floor? If you can introduce yourself with your question, that would be great.
Hi there, I'm David Leto from University of Calgary. So I think what you've done is really cool, especially considering how much time it takes to put together these animations. Now, the question that I have is, when you look at animators, there's this fine-tuning that they do to apply principles of animation to make it more expressive. Mm-hmm. And so what I'm wondering is, how does this tool fit so that an animator can take that and actually fine-tune all these different aspects of the motion so that it'll be more towards what they actually want? Mm-hmm.
I think the main value of the tool is in first providing them with the inspiration, because we have created a data set that can show them what are various options that they can use, various styles that they can use to convey a particular emotion. And then the parameter sliders that I was showing really do allow them to do finer editing. They need not use the automatic slider, but they can really edit a single parameter at a time, and this gives them finer control. I did not talk about this a lot, but there is also ways to log the parameters which they do not want to change, so that will make sure that the system keeps them fixed while they change the other parameters and see how that affects the motion.
And could they, in theory, take that to a different tool, like something like Maya, to actually manually move the small pieces that they might be interested in?
So do you mean we can export the things to Maya?
Or to something else?
What we can export right now is joint angles, like time trajectories of different joint angles. I think that should be possible to import in Maya if the robot models are matched. So if you have a robot character which is rigged and has the same joint angles.
Okay, thank you.
We have time for one more question if it's a short one. Do I see any hands?
Hi, Edith Law from University of Waterloo. I was wondering how this might transfer to humanoid robots and whether it can do similar things with, say, verbal behavior instead of just motion behavior.
What was the last part?
Whether you can explore, like use this tool to explore spaces of verbal behavior as opposed to motion behavior.
So, the tool will directly work for motion behaviors of humanoid robots. All you need is a simulation that can generate motions of the humanoid robot and the corresponding parameters, and you can basically run it through the framework or the pipeline, and it will work. For verbal behaviors, that's a very interesting question. I don't know how to parameterize verbal behaviors, but I think the general idea of mapping them to sampling them and figuring out if we can create a mapping that allows us to semantically explore the space should be interesting to explore for them, but it definitely needs more research.
Thank you.